okay? They're all needing oxygen to go in, and they're all producing CO2. Is everybody with me on that? Okay. We always have in the capillary bed the arterial end, the venous end. On the arterial end, oxygen can be dropped off. Venous end, CO2 picked up. Okay, is everybody with me? The amount of oxygen that will be dropped off will be dependent on how active these cells are. So due to cellular respiration that's taking place, which is occurring, okay, gets increased when the tissues get active, okay? That means in these tissues where I find my extracellular fluid, okay, that extracellular fluid is where the oxygen ends up being so that the cells that need it pick it up. Cells that produce the CO2 put it into the ECF and it goes back to the venous end. Okay? Everybody with me? Now, this means in the tissue itself, oxygen demand will be high, CO2 buildup will be high, okay? We got to have it dropped off, we got to get the CO2 picked up. So based upon how active the tissue is, meaning making ATP for energy at that cellular level, will determine how much oxygen gets dropped off. So if that was a metabolically active tissue, they may be demanding 3 oxygens off of that hemoglobin. So that would be a 75% demand. Does that make sense? Okay, but I got to have a high pickup rate also. Okay, so the more metabolically active, the more oxygen there is for demand. So when the CO2 gets picked up, my red blood cells, like I was saying, they help buffer the CO2. They have an enzyme called carbonic anhydrase. You guys remember ASE to represent an enzyme? So therefore, anhydrous water, okay? Carbonic against that CO2. Now, something that we got to deal with. The bicarb ions get exchanged for chlorine. This is one of the very few times we see chlorine utilized in the body. Do you guys remember how when we take in salts, such as sodium chloride, we've always talked about the sodiums, the potassiums, the calciums, the magnesiums, but they're all stuck to a chloride ion. Have you ever wondered what happens to the chloride ion? This is one of the very few, I'm talking like 2 to 3 times throughout the body that the chloride ion is used. So, it's called the chloride shift because of the exchange that takes place. This helps to buffer those H pluses and therefore we don't affect the pH of the blood. That is the goal. Do not affect the pH of the blood. So, oxygen, if we can buffer, therefore, oxygen loading, once we get back to the lung tissue, this buffering that took place in the blood, what it's going to do, it's going to release the CO2s. That increases my demand for oxygen. Oxygen will move to my red blood cell. One of the things about my oxygen availability, there is a lot of oxygen available in the blood because of what remains in our venous system. Remember, arteries are under pressure. They do not reserve anything. Veins do. They keep roughly about a 5-minute supply in backup. That's why, in the case of a severe injury, loss of consciousness, something along those lines, that 5-minute time frame becomes important. Because at that point, if you haven't restored or stopped the blood flow, restored consciousness, whatever the case might be, at that 5-minute time frame, we know oxygen levels have dropped severely in the body. Tissues are getting deprived, especially tissues of the brain, and therefore lead to the death of the tissues, possible brain and y'all help me with brain damage. I couldn't get the term out. Okay, possible brain damage in the case of these emergency situations. So we have a backup of oxygen, if that makes sense. So now, here's what's happening. Let's take it apart. Okay? First of all, this is what's going to happen in my systems. Meaning, blood has left the heart and is making its way around the body, getting dropped off at tissues and so forth. So, if these are my tissues, all right, see how they're trying to represent all the little tissues here, the little cells? CO2, CO2, CO2. These are the 3 ways, the 3 forms that we can carry or transport CO2 in our body. We can transport CO2 as a dissolved gas. Very little is transported in this way. About 23% makes its way to the red blood cell. Do y'all see how they are showing that represented? Okay? The majority of the CO2 wants to get into this red blood cell, be exposed to that enzyme, get to being a bicarb and the H+, and go through the chloride shift. That's the majority of the way that CO2 wants to travel. It can travel under the CO2 meeting up with a protein in my plasma. This is called carbamino compounds. Okay? They actually test that. Different lung disorders and so forth. But the majority of it wants to become the bicarb and help be buffering the blood. So at the systemic level, CO2 gets picked up. Once again, if the CO2 is high and we've gone through the chloride shift, that is signaling to the red blood cell that there's a high demand for oxygen, and look what happens. Almost 100% gets dropped off from that hemoglobin. Does that kind of make sense in that picture now? Based upon the demand of that tissue would affect the percent of the oxygen. So if that tissue was not metabolically active, it might be only 50% of the oxygen gets dropped off. Maybe it's only 25%. So therefore, the activity of the tissue, the CO2 produced, the amount that will become a bicarb, create the chloride shift, will determine the O2 that gets dropped off. This is stuff that actually gets measured. Take a break. Be back at 9:30.